Okay. So in the last class, I think I have explained about the parameters of the radar. Okay. It is if you take the parameters of the radar means if you take the range, it is it is unambiguous range is PRT, okay, PRF, okay, it is etc etc. So all those are the parameters of the radar here. Okay, it is what do you mean by the range and what do you mean by the PRT, what do you mean by the PRF, unambiguous range already so has been studied in the previous class. Okay, and if you take the continuation of that one, so in this class I am going to explain about it is a radar range equation. Okay, it is what is the equation to calculate the range of the radar here. Okay, so in this class, I am going to explain about it is a radar range equation and it is what are the factors influencing the radar range equation. Okay, so if you take the radar range equation, it is to be considered, it is based on the transmitted power and it is based on the received power. It is based on the strength of the transmitted signal and it is based on the strength of the received signal. And if you take the ratio of that one, so that means that if you obtain the gain, it is itself is going to represent the radar range equation. Okay, suppose consider that what this radar range equation is useful to understand the maximum range of the radar. Okay, that can it can be detected by the radar. It is with their performance parameters. Okay, already I think you know about the parameters here. It is based on the it is performance parameters only, so that the equation of the radar so has been implemented here. So if you take the power density at the range R, it is from an isotropic antenna is to be given by it is PT divided by it is 4 pi R square, which is to be represented in terms of the watt per square meter. Okay, this is indicating it is density of the power, it is of the isotropic antenna. Isotropic antenna means if the signal is to be radiated in all directions. If you take the power of the signal in the all direction means it is to be given by the equation it is pt divided by it is 4 pi r square. R is the range, it is pt is the transmitted power. Okay, if you take the maximum gain of the antenna, it can be defined as it is gain is equal to it is maximum power density, it is radiated by an antenna, it is to be divided by it is power density, it is radiated by the lossless isotropic antenna. Okay, if you consider it is the maximum power, it is which is to be radiated by the antenna itself. After radiating, if you consider it is a signal power in all directions, okay, and if you take the ratio of that one, it is going to give you the gain of the antenna here. Understood? Okay, if you take the power density at the range R, it is from an isotropic antenna is to be given by it is pt divided by it is 4 pi r square. I think you know it is what actually it is 4 pi r square. It is the area of the circle. Okay, it's nothing but the antenna. What this pt is, it is the transmitted power. Okay, and if you take the gain, it is to be given by the equation it is maximum power density, it is radiated by an antenna, it is to be divided by it is power density, it is to be radiated by the lossless isotropic antenna. In the yesterday's class I said that it is what the maximum power and it is what the isotropic antenna power. If you take the peak power, it is called as the maximum power of the antenna. And if you take the average power, it is to be calculated based on the isotropic antenna. Okay, it is based on that one. If you take the ratio of that one, it is going to give you the gain here. Okay, and after that, uh, if you take the power density, if you take the power density at a range or from a directive antenna, so that means that if you are going to consider the peak power, okay, in the yesterday class, this while explaining the it is parameters, I have explained the definition of the peak power and the average power. Okay, if you take the peak power, it is to be considered to the directive antenna. And if you take the what? Average power, it is to be concerned for the isotropic antenna. So that if you take for the peak power means if you take the power density at a range R from it is the directive antenna, it is to be given by it is PT into G divided by it is 4 pi R square. Already you know it is what actually it is PT divided by it is 4 pi R square. It is it is the power density of the isotropic antenna, and if it is to be multiplied with the gain G, it is itself is going to give you it is power density at the range from a directive antenna. Okay, the earlier two equations is to be get multiplied here. It is PT into G divided by it is 4 pi R square. PT into G divided by it is 4 pi R square. Okay, this is about the transmission. After a transmission, a signal is to be reflected back there. Okay, so for that purpose, if you take the reflected power, it is from it is target, it is towards the radar, it is the transmission power. If you take the reflected power, it is to be given by it is PT into G divided by it is 4 pi R square. Same thing into it is sigma divided by it is 4 pi R square. Out of the number of radiated signal, it is going to reflect only the part of that one. So it is whatever the transmitted signal, if it is to be multiplied with this factor, it is going to give you the reflected signal. Okay, and if you take the radar antenna receives a portion out of the reflected signal, it is going to receive only the portion of that one. So how much amount of the portion it is going to receive, again it is to be decided by the antenna size. So it is what the radar antenna receives a portion of the reflected power, it is from the target, it is cross section. So if you take the received power can be given as this PR. If you take the PT is the transmitted power. If you take the PR is the received power. This PR is equal to it is PT into G divided by 4 pi square into it is sigma divided by 4 pi R square into AE. In this what AE is the effective area of the receiving antenna. If the reflected power density is to be get multiplied, it is with the effective area of the antenna, it is going to give you the reflected power. Understood? Okay, and after that, if you take the maximum range of the radar R max, it can be defined as the maximum distance it is behind which the radar it cannot detect the range. So in this case, R is only the range here, and it is what is its maximum value. So the maximum is the one up, so above which it can't able to detect. It should able to detect it is only it is within the range. So R itself is to be represented as an R max here. So the value of the R itself is represented as R max. So if you take the S min is equal to it is PT into G divided by 4, it is pi R square into sigma divided by 4 pi R max square into AE. R itself is changed as an R max. And if this equation has been simplified, and if it is to be indicated as an R max, if you take to calculate for an R max, it is equal to PT into G divided by 4 pi into sigma divided by 4 pi into AE divided by S minimum. Okay, it is whole to the power of 1 by 4. This is the fundamental form of the radar range equation. This is the equation of the radar. And if the antenna is used for it is both the transmission and the receiving purposes, it is then the it is transmitted gain can be given in terms of an effective area. It is where the G is equal to it is 4 pi AE. It is to be divided by it is lambda square. Okay, so it is to be given as it is equal to G is equal to it is 4 pi AE divided by okay lambda square here. Okay, and after that the equation can be given as R max is equal to it is PT G square okay lambda divided by 4 pi whole cube into sigma into AE divided by S min, it is whole to the power of 1 by 4, in which what this gain the G is assumed to be the constant. And another equation, it can be considered as R max is equal to, it is Pt divided by 4 pi square into sigma into Ae square divided by S min. It is whole to the power of 1 by 4 in which the AE means the effective area of an antenna is assumed to be the constant here. So what these three forms of the radar range equation are based on the effective area and the transmitter gain G. This is the first equation. Okay, this is the second equation. This is the third equation. All of these three are the equations of the radar range. Understood? Okay, I'm going to repeat in brief. If you take the power density of the isotropic antenna, it is to be given by, it is Pt divided by 4 pi r square. If you take the gain, it is to be given by, it is maximum power density is by an antenna to be divided by, it is power density by the lossless antenna. Okay, it is to be considered for the isotropic. And if you take for, it is the power density for a single direction, so it is to be multiplied. Okay, these two is to be get multiplied. After multiplying these two, it is equal to Pt into J, it is whole divided by is 4 pi r square. And if you take the reflected power, it is equal to Pt, okay, G divided by, it is 4 pi square into, it is to be get multiplied. And out of this reflected power, it is going to receive only the portion of that. Only the portion of that one means it is to be multiplied. So if you take this equation, is to be get multiplied by the effective area of the antenna. And after that, you can able to get, it is the actual received power or it is a reflected power. And this is, if this equation is to be considered for the maximum range, it is indicated as an R max, and it is itself is acting as the fundamental form of the radar range. And again, if you take the one more, it is equal to G is equal to 4 pi into AE divided by, it is okay, lambda square. It is because a single antenna is to be used for the transmitting purposes as well as for the receiving purposes. Okay, so that you are using the duplexer there. So for that purpose, if you consider this equation and if it is to be placed in the above equation, so that you can able to get, okay, this R max in, so in terms in which the G is constant, and the another equation in which AE is assumed to be the constant here. So all of these three equations is assumed to be the fundamental, okay, radar range equation. Understood? If you take the factors influencing the radar range, okay, it is what are the factors affecting the radar range. So if you take the main factors, okay, that influence the range of the radar equation are, it is frequency, okay, peak power, if you take the pulse width, okay, PRR, it is beam width, okay, target characteristics, okay, receiver sensitivity, and the antenna rotation rate. Okay, all these are the factors influencing the radar range equation. Okay, so and after that we'll see all these one by one here. It is what happens if the frequency alters here. So if you take the higher the frequency of the radar wave, what the greater is the attenuation. The increasing in the frequency is going to, it is loss of the power, so the signal is going to be get attenuated. If the frequency is of the less, it is going to give you the very good power. So it is regardless of the weather. Okay, it is lower the radar frequencies. Okay, it has been gradually, it is superior for the longer distance. It is a detection ranges. Increasing in the frequency, it is going to decrease its range. And if the frequency is going to get decreased, it is going to increase the, it is a range, identification range. If you take the peak power, if the peak power of the radar is its the useful power, okay, out of the isotropic radiation, it can able to consider only the single direction I said. So if we take the single direction power, it is itself is the useful power here. So if you take the range capabilities, if you take the range capabilities, and it is going to double the peak power, it is by increasing in the range capabilities, it is by 25%. If its power is to be get doubled, it is going to increase its peak power, it is by 25%. Okay. And another one, if you take the pulse length, it is longer the pulse length, it is greater is the range of the capability of the radar. It is because of the greater amount of the energy transmitted. Obviously, increasing in the pulse, it is going to increase the range here. Okay. And if you take the pulse repetition rate, it is PRR. It is going to determine the maximum, okay, measurable, okay, range of the radar. The ample time is must be allowed between the pulses for an echo to return. It is from any target to be located. It is within the maximum, okay, workable range of the system. Otherwise, the echoes returning from the more distant, okay, targets are blocked by the succeeding transmitting pulses. It means that after transmitting the signal, so it should have the sufficient waiting period in order to receive the reflected signal, or else it is going to enter into the unambiguous range. If the ample time has not been given, okay, it may able to receive the echo signal after the transmitting of the second pulse. So what this pulse, okay, repetition rate, it should be high. Okay. And if you take the beam width, it is going to represent the bandwidth here. Okay. What this beam width, so it is more concentrated the beam, it is having the greater detection range of the radar. Obviously, increasing in the width, it is going to increase its detection range, obviously. And if you take the target characteristics, again, if the target body is to be arranged on the LOS, it is a line of sight, it is going to give you, it is exact better performance. And outer body of the target, if it is going to be implemented with the metal, it can able to reflect the signal effectively. And if it is to be made up of the insulator material, means it can able to get, it is of the poor reflection. I think you know that if you take the microwave signal, it is to be get reflected with the metals. Yes or no? Okay, if it is to be get reflected with the metal, means if the outer body is made up of the conducting material, it can able to give the exact perfect reflection. And if it is to be made of the insulating material, either of the glass or of the wood, means so what that reflection, it may get decreased here. Okay. So if you take the targets that are large, it can be seen on the scope of, at the greater ranges. It is provided, it is line of sight exists between the radar antenna and the target. And if you take the conducting materials, a ship's steel hull for an example considered, it returns, okay, relatively, it is strong echoes, it is, while the non-conducting materials, it can, okay, return the weaker echoes. Okay, if it is to be implemented with the conducting material, means it is going to give the strong echo signal. And if it is to be implemented with an insulator material, means it is going to give you the poor echo signal or the weaker echo signal. Understood? This is about, it is target characteristics. And if you take the receiver sensitivity, so it is more, okay, sensitive receivers is going to provide, it is greater detection rate, it is a range, it is, but or it is more subject to the jamming. If the receiving capacity is more, means it can able to grab the signal, it is effectively. And if it can able to grab the signal, it is effectively, means it can able to grab, it is more than one signal also. At that time, it can subject to the jamming also. Okay, now. And if you take the antenna rotation speed, if the antenna, if it can able to rotate in the slow, it can able to catch the reflected signal very easily. And if its rotation is with the high speed, means it is of the weak in catching the reflecting signal. Okay, so it is more slowly the antenna rotates. It is greater is the detection range of the radar. It is apparent that at the higher antenna rotates, the maximum ranges at which the targets, it is particularly the small targets, it may be detected or to be reduced. Okay, it is exception or what is that grabbing of the signal is to be get decreased if the antenna rotation speed increases. Okay, so all these are, it is parameters, or all these are the factors affecting the radar range. Okay, initially it is frequency. If it is of the higher frequency, okay, it is having the attenuation. If the frequency is less, it's not having the attenuation. Attenuation will be less. And if you take the peak power, it is a doubling the peak power increases the range capacity by, it is 25%. Okay, if it is going to be get doubled, so it is going to increase its range by, it is 25%. And if you take the pulse length, increasing in the pulse length increases the range capability. If you take the pulse repetition rate, again increasing in the pulse repetition rate period increases the maximum measurable range. And if you take the beam width, increasing in the beam width again increases the range with the concentrated. And if you take the target characteristics, if it is to be implemented with the conducting material, it can able to give you the strong reflected signal. And if it is to be implemented with the insulating material, it is going to give you of, it is weaker echo signal. If you take the receiver sensitivity, if it is of the, it is highly sensitive, it can able to receive the signal, it is very easily. And it can able to receive, it is more than one signal also, it is subject to the jamming. And the antenna rotation, if it can able to rotate under, it is less speed, it can able to receive the signal very easily. And if antenna rotation is speed, okay, its detection is going to be reduced. Okay, all these are the factors influencing the radar range. Understood? Okay, in this class I have explained about the radar range equation, and it is what are the factors influencing the radar range equation. If you take the possible questions on this concept is, he may ask you to explain the radar range equation. So it's a derivation is to be done, or he may ask you to describe the factors influencing the radar range. So these are the possible questions. So in the next class, we are going to explain, I am going to study, or I am going to explain about it is pulsar radar system. Okay. Okay, thank you.